In this video, we're going to introduce the concept of force and talk about how forces can combine to give an overall net force or cancel out and result in equilibrium. So to start us off, let's remember some of the fundamental SI units. There's a list of 7 official SI fundamental units. Now that didn't really make sense as much when you're talking about them by themselves, but it makes a little bit more sense as a concept if you combine it with something known as derived units. So to do this, we're going to use an analogy of primary and secondary colors. If you remember your elementary school math class, the primary colors are red, yellow, and blue. Now, if you combine those colors in different ways, you can get the secondary colors like yellow and red combine to give you orange. Secondary colors are any colors that use the primary colors to create new colors. Now, with those three primary, you can create essentially any color by combining them in different ways. The same is true with units. We can take our 7 fundamental units and combine them in a variety of different ways to get a bunch of different derived units. Sometimes it looks like this. Velocity is meters per second, or acceleration is meters per second squared. Force is measured in newtons, but that means kilograms times meters per second squared. So just like we call orange, orange has a name, not the mixture of red and yellow. Newtons has a name, but it is the mixture of kilograms, meters, and seconds. So we can make any derived unit using our fundamental. Today we're going to be looking primarily at our force unit of newtons. So what is a newton? Well, essentially, a newton is a unit of force. As we described, Newton is represented as kilograms times meters per second squared. Now, the challenge with newtons is it's a unit that we didn't necessarily grow up with, so we don't have a great conceptual framework of how big a newton is. So here's one that I like to use. If you imagine holding your hand out and then an imaginary apple being placed in your hand, that weight of the apple is approximately 1 Newton. So if you're holding an apple, you're going to be pushing up on that apple with about 1 Newton of force. So if someone were to say you push on the box with 25 Newtons of force, imagine holding a basket of 25 apples. That's about what we're talking about. So it's useful to have a concept of is that big? Is that small? This will give you a framework. Now, as a reminder, vector and scalar quantities are still a thing. Displacement is our vector, distance is a scalar. Velocity is a vector, speed is our scalar. Vector units, vector quantities are something that has a direction in addition to its magnitude. We are going to add force to our vector category, and later on we'll see energy as one of our scalars. This is not a hard, fast rule, but oftentimes vectors might have a direction indicated by a negative whereas scalars are typically only positive. Again, that breaks down at a certain point, but most of the time we can think of it in that way. Now, force, we typically don't think of it in just the positive or negative direction. It's all sorts of directions. So we're going to describe force using a bunch of arrows, and the direction of the arrow is the direction that the force is being applied. Throughout this unit, we're going to see many different types of force. All of these forces are basically described using a capital F and some subscript that gives us a description essentially of what we are looking at. We will hit several of these in the coming videos as a way to describe the different types of forces and where these forces might be coming from. For now, we're not going to worry too much about specifically what force they are. Instead, we're going to draw all of the forces that are acting as unlabeled arrows. We might label the amount of force, the magnitude, but not necessarily the identity of that force. Now, when we draw a free body diagram or a force diagram, sometimes referred to as a FBD, we draw the vectors originating from the point that represents the center of the mass. And typically, we draw every box or every object as a simple square, a box. That could be a giraffe, it could be a race car, it could be a hot air balloon. They are all going to be a box. So you might see arrows that look like this. You might see arrows that look like this. These are free body diagrams representing just the object, not the surface, not any external things, just the object and the forces being applied. So when we have more than one force, it is helpful to us, especially when we get into motion, to be able to describe one force, one overall force that's acting on the object. We call this the net or resultant force. You can think of it as basically the total. It's the sum of all the forces. Now, it's not as simple as just saying 5 plus 12. You have to look at the direction. So if I got 5 going to the left, 12 going to the right, it's going to give me a net force of 7 newtons to the right. The 12 is larger than the 5. If I have 5 and 12 both going in the same direction, 7 plus, or 5 plus 12 is 17 newtons. Notice my vector is longer, pointing to the right. Here, these vectors are just describing the direction of that net force. Is not always required, especially if you're being asked for the magnitude. It's just how much is that force. So notice, these are both 5 and 12. They result in different net forces based on the directionality of those original forces. Now, we can take this to the extreme and say, well, what if the 5 and 12 weren't going perfectly together or perfectly opposite? What if one was going up and one was going to the side? Now, conceptually, you probably have an idea of what would happen. If you push to the side and your friend push up, it's going to go upward kind of at a diagonal. The way we can resolve that is we think of, okay, the overall net force is going to be a force 5 in the vertical and 12 in the horizontal. So it'll give us some diagonal that represents both of those directions at the same time. Now, we can think of this as a triangle and basically say, all right, 12 in the horizontal and 5 in the vertical, I get a hypotenuse of that right triangle of 13. It's a 5, 12, 13 triangle. If you want to use Pythagorean theorem, you can do that. 5 squared plus 12 squared equals 13 squared. So we're going to call that a net force. We could use trigonometry to calculate the angle, but for now, we're just seeing that 13 newtons is my overall force. So again, we saw that 5 and 12 could have given us 7, or 17, or now 13. There are a variety of different examples if we had slightly different angles here that would get us something in the middle as well. So if we have all of our forces that are acting and giving us a net force, there should be scenarios that those forces cancel each other out. We're going to call that equilibrium. So say we have this kid swinging on a tire swing from the time of his life. He has a weight of 200 newtons going down. If he is in equilibrium, that single rope must be supporting that 200 newtons now pointing upward. The 200 times plus 200 in opposite directions cancels out for a net force of 0. Here we have a kid swinging on the loneliest swing set of all time, but this one has 2 ropes, which means each rope will be that 100 newtons of force. So 100 plus 100 equals 200. I still get a net force of 0. In all of the examples today, we are going to see equilibrium playing out, which means no matter where the forces are pointing, they will all cancel each other out in some way. So let's look at another example. Here we've got a window washer setup. We've got one washer is one guy is 750 newtons. The other one is 800 newtons, and the platform itself is 900 newtons. Now, there are 2 ropes here. Let's say one of the cables is 1350, and the other cable is represented as T. We should be able to calculate what T is. On the swing set, we had both ropes supporting exactly the same amount. We were imagining that that kid was perfectly in the center, being supported equally. That doesn't have to happen. You can lean heavier on one side versus the other, and that's what's happening here. We do know that the bottom, the down, has to equal the up. So an overall net force of 0, my upward force, 1350 plus T, should equal the downward force. So if I subtract, they're in the negative direction, if you will, these other forces, it should give you 0. Using some algebra, we can calculate that T would be the remaining 1,100 newtons. Now, of course, 1,100 newtons plus 1350 should add up to the total weight of the washers plus the platform. So when we have an object that is in equilibrium, it's going to undergo and be following Newton's first law. Now, you might be familiar with Newton's first law. A body at rest will remain at rest or moving with a constant velocity unless it's acted on by an unbalanced force. Now, you may have seen this in a couple different examples. Maybe you've seen somebody do the tablecloth trick where an object at rest stays at rest, then you pull the tablecloth and the object remains there. You may have seen this in the case of like momentum where a semi truck is slowly creeping forward. Hard to stop because that body is in motion. And if there is not a net force, an unbalanced force, it's going to keep going. This idea has a name. We call it inertia. So Newton's first law is the law of inertia. In all of these scenarios that are in equilibrium, the object will just remain. It'll continue doing whatever it's doing. That might be remaining, not moving. A lot of our situations are static that we'll see, but it might also be moving at a constant velocity and just not changing its motion. And we'll get at some of those examples as well. To do this, we are going to need to talk about forces that are in two dimensions. We saw this a little bit by taking that 5 and the 12 and making a triangle. Here, let's imagine that we have a 20 Newton force that's up at an angle. And let's say that that angle is 30 degrees. Well, part of that force is in the horizontal direction. We'll call that X. And part of that force is in the vertical direction. We'll call that Y. So what we did before was we combined an X and a Y to give us the magnitude of that diagonal. Now we have the diagonal, we need to split it back up into an x and a y. To do this, we need to use sine, cosine, and tangent. You have to remember your trigonometry rules. So here, if I wanted to find one of these, let's say I wanted to find x. X is my adjacent side. So the cosine goes along with adjacent. Cosine of 30 will be x over 20, the adjacent over the hypotenuse, which means if I solve for x, it'll be 20 times the cosine of 30, which is 17.3 newtons. I do the same thing for y. Y is my opposite side, which means I'm going to have to plug that in with sine. The sine of 30 is y over 20, so y is 20 times the sine of 30, or 10 newtons. So the sine of 30 will always give you half the hypotenuse. We can take this and turn it into an equilibrium problem. So let's say we have that same 20 Newton force at 30 degrees, but now we have a 10 Newton force going down and some mystery force going to the left. If you are told that the object is in equilibrium, all the forces have to cancel. In two dimensions here, it means the downs have to equal the ups and the lefts have to equal the rights. Basically, every direction should cancel. It gets a little trickier when you have an angle here. So we can imagine, like we did before, that part of that is x and part of that is y. And if you split that up into an x and a y, we don't have an angle anymore that we have to worry about. So let's imagine instead that our free body diagram looks like this, that we have 10 down, some unknown to the left, and then some amount going up and some amount going to the right. That amount up and to the right is all coming from this 20 newtons. And we calculated that before. We said it was 17.3 to the right and 10 newtons going up. Now it's really easy to see what this has to be in order for everything to cancel out and be equilibrium. 10 up and 10 down cancel, which means my unknown force has to be that 17.3 to cancel out my x direction of that 20 newtons at 30 degrees. So let's look at this in another example. We'll see several examples here. This is a situation where you have a force going down and two forces going up, 50 newtons, each at a certain angle. This is also going to be net force of 0. Let's define that angle as 45 degrees. Now, this isn't all that different than the kid sitting on the swing with two strings. This force is going to be evenly distributed among these two tensions or these ropes, if you will. Each one has an x and a y, and we can calculate what that is. 35.4 in the x direction, 35.4 in the y direction. Notice here, sine and cosine both give you the same thing. That 45 degree gives you an isosceles triangle. Now, since the other force is exactly the same, we can draw that 35.4 going to the side and up over there as well. As we did before, now that we have our components, we've resolved those components, we can redraw this, not worrying about those 50 newtons at an angle. We've redefined them as an x and a y. So let's draw it like that. Let's say we've got 35.4 going in either direction. 235.4 is going up. And then we need to figure out this mystery. The 35.4 to the side, that cancels, which means my downward force is to cancel out that double 35.4 newtons to give me something in the ballpark of 70.8. Now, there's a little rounding that's happening here. If you don't round it, you might get something closer to 70.7, but you get the idea. Here, we are supporting that force by these two forces, but only the vertical part is supporting that vertical down. All right, let's stick with this concept of supporting with this angled tension. Here is a sign that is 300 newtons of weight being supported by these two cables. Again, let's assume that those cables are both supporting the same amount. In this case, is not like the swing though. We're not going to say each one is supporting exactly 150 newtons of tension because that tension is not going in the same direction as the 300 newtons going down. So let's redraw this and say, well, those angled, those 27-degree forces, well, that's partly up, but also partly to the side. We know the up part should cancel out with this down part. So assuming that they are the same, Let's say that the up part is going to be that 150 newtons, half the sign's weight. So just looking at one of these cables, if that triangle, it gives us that 27 degrees, we must be able to support that using this sine, cosine, tangent. So 150 degrees is opposite the 27, which means it goes with a sine. If I rearrange that, the force times the sine of 27 gives me 100 degrees or 150 newtons, which means the force on this rope is 330.4. What that means is essentially this picture. Now that feels kind of wild that each one of these ropes, these cables, is supporting a stronger tension, more force than if you were to have just one single rope going straight up supporting that sign all by itself. And that is all because of the angle and what needs to happen in order to get that vertical to the 150 newtons that's required. So this can be thought of as basically the strongman physics. So here I've got uh, a wrench, a monkey wrench that's fairly heavy, and a rope. So typically, if I were to support this like this, the rope you can see is pretty angled. If I pull very hard and try to get it perfectly perfectly horizontal, it gets close, but you'll notice no matter how hard I pull, it still sags a little bit in the middle. Turns out it is impossible to pull hard enough that it'll be perfectly horizontal because you need a vertical component of that force in order to support the vertical component of the weight. It is not possible that it could be perfectly horizontal and still be able to support an upward load because there would be no vertical component. And that means that the more horizontal it is, the greater tension is required because that angle is so slight that you would need a really, really big magnitude of the force in order to get a big enough vertical component. All right, let's look at one last problem. If I have a free body diagram that looks like this, and the thing that I don't know is the angled force, as long as I know the angle, I can figure out what's going on here. Actually, I don't even need to know the angle. I know that this force of tension is partly X and partly Y. Here I know the other two forces. I know that in the X direction, I've got 90 newtons, and in the Y direction, I've got 150 newtons. If I plug that in, and say, all right, the Y is supporting that 150 and the X is supporting that 90, I can now recreate my triangle and put that back together and say, well, that triangle has sides of 150 and 90. That is Pythagorean theorem. 90 squared plus 150 squared equals the force of tension squared. Square root everything, and you get about 175 newtons, which is pretty cool that you can take all of these pieces and figure out what your overall force of tension is going to be. So in this video, we looked at all of these different examples of how forces can be applied on the same thing to get a net force, and ultimately, if they all cancel out, to give us equilibrium, and understanding how the angles play into calculating all of those pieces.